Okay, so we're going to start with a quick welcome, some announcements from CMS while people join in. This is part of the NASA Carbon Monitoring System CMS Policy Speaker Series. Today, we're very excited. We have two speakers that are going to be talking about a topic of a lot of interest for the CMS scientific and stakeholder community, that is blue carbon. And we're going to have a presentation integrating blue carbon into state climate planning and coastal management, overview, opportunities, and needs. And we have Sylvia Truss with the Pew Charitable Trust and Laura Brophy with the Institute for Applied Ecology. Before starting with today's presentation, just quickly for those of you that don't know, obviously this initiative is the Carbon Monitoring System initiative from NASA. We have archived more than 100 data products. We have been ongoing funding projects for more than 10 years now. A couple of products that we have available in the Oak Ridge National Lab DAG that are relevant for the blue carbon community. We have this global mangrove distribution above ground biomass and canopy height product that was updated in 2021. This is a project that was led by Lola Fatoyimbo here at NASA Goddard Space Flight Center. Also, we have a very recent product from late last year, December 2022, that is Global Salt Marsh Change from 2000 to 2019. Besides these projects, we have a couple of active projects that are funded through CMS. Monica Moscal with this steel carbon stakeholder driven monitoring of forested wetland carbon. She has been working in the Pacific Northwest coast, and she has been engaging a couple of state agencies in Washington. This is very relevant for Sylvia, the part of your talk that you're going to be talking about. We have James Holmquist, we have Ben Poulter with the Blue Flux project that they have been collecting data in southern Florida just recently. And then also another project prototyping a monitoring system of global wetland methane emissions with machine learning and satellite remote sensing. And we hope we're going to announce in a couple of days or maybe weeks new projects. I think we have 15 to 17 new CMS funded projects, and a couple of them are on blue carbon. So stay tuned for that. For those of you that want to know more about the program, you can visit our new website. It's the same URL, carbon.nasa.gov, more interactive with visualizations. And there you can see also how we're engaging with stakeholders, and some of the success stories engaging with stakeholders and how stakeholders are using CMS data products. Here you can see just a couple of examples. Quickly, in the website, you can also find our recently published CMS Phase 2 synthesis report, scope, findings, gaps, and recommended next steps on the program. A couple of important dates. We have the CMS Stakeholder Workshop that is coming up September 26, Pasadena, California. The Science Team meeting following that, September 27, 28, also there in Pasadena, California. We're going to send more information about that to the CMS community. And then we're going to have CMS sessions, oral and posters during the AU fall meeting that is going to happen in San Francisco later in December. As always, we mentioned if you want to publish a paper, we have this special edition in ERL on carbon monitoring system research and applications. So take a look at that. I'm not going to be talking about this. This is a recent workshop that we had between NASA and US Forest Service that CMS is very involved. But if you want to learn more about that partnership that CMS is working on, you can visit aoip.com. That's the Applied Earth Observations Innovation Partnership. And then with those announcements, we're going to go and have the presentation today. We're honored to have Sylvia Truss. She's the Senior Manager for Conserving Marine Life in the United States Project at the Pew Charitable Trust, and Laura Brophy, the Director of the Study Technical Group at the Institute for Applied Ecology. We're going to have Sylvia first presenting, and then Laura, and then we'll have at least 15 minutes for the Q&A and discussion with you all. So without further ado, I'm going to leave you all with Sylvia, and I'm going to stop sharing here, Sylvia, and you can share.
Great. Thank you, Adil, and thank you to the CMS policy briefing for inviting Laura and me to talk today with you about blue carbon. So as Adil said, I'm Sylvia Truss. I work for the Pew Charitable Trust, and I oversee a project that aims to elevate the conservation and restoration of coastal blue carbon habitats. So this includes salt marshes, seagrasses, and forested tidal wetlands into state climate planning. And I will share my screen now. All right. Everyone see my screen okay?
Yes.
Yes. All right. Great. Thank you. All right. So I'm going to talk a bit about the policy context within which we are working and what's happening with some of the states where we're engaged. And then Laura will talk more about the science and data and research work and needs that underpins all of this effort. So I'll start here with this slide. Most of you may have seen this, but I think it's a good slide that explains why states in the U.S., some states in the U.S. and countries are increasingly looking at their natural working lands as a pathway to help advance climate mitigation goals. So though not a substitute for reducing emissions, improved management of natural working lands can be an important piece of climate response strategies. And so this is a relatively new policy arena, the natural working lands policies, and the U.S. Climate Alliance really kind of catalyzed this effort. The U.S. Climate Alliance is a governor-led coalition of states that are committed to advancing the goals of the Paris Climate Treaty. And so states that are involved in the U.S. Climate Alliance are in various stages of developing these natural working lands strategies. And, you know, for two major reasons. One, as you saw on the previous slide, there can be significant greenhouse gas mitigation potential in this sector. But secondly, actions in this area can also derive significant co-benefits, and I'll get into some of that with respect to blue carbon. All right, so what are these natural working lands plans? So these refer to actions on landscapes like forest landscapes, grasslands, working landscapes like farms and ranches, wetlands, which is where we come in, and even California is also looking at desert landscapes. And so these plans include specific actions that aim to reduce emissions, avoid emissions, and expand carbon sinks. So these plans typically include a carbon assessment, and so these can be more basic assessment of existing carbon stocks, but can also be more sophisticated inventories of greenhouse gas emissions and removals coming from these landscapes. And these estimates are then used to help inform management strategies and set specific targets to reduce and avoid emissions and enhance removals. So basically to help move beyond business as usual to advance climate goals. And these plans, because the states that are doing these have specific climate goals, greenhouse gas mitigation goals, they're tracked over time to assess progress towards achieving those goals. All right, so I'll turn now specifically to blue carbon. So when Pew started this work in 2021, we recognized that natural working land strategies were not including actions related to coastal habitats, despite the fact that urgent action is needed to stem the loss and bring about recovery of these ecosystems. There seemed to be a disconnect between growing research and knowledge on the ground about blue carbon with climate planning efforts. So Pew saw an opportunity to step in and help connect these efforts. So just by way of background, vegetated coastal blue carbon habitats like salt marsh, forested tidal wetlands, and seagrass are recognized by the Intergovernmental Panel on Climate Change for their greenhouse gas mitigation benefits. And research has indicated that on a per acre basis, these habitats can sequester and store carbon at rates either on par or exceeding those of tropical forests. And if left undisturbed, they can continue capturing and storing carbon for millennia. Conversely, if coastal wetlands are degraded or destroyed, they can release centuries worth of stored carbon back into the atmosphere. So that obviously is not good for climate change. So this growing body of research, coupled with the fact that starting in 2017, EPA is including coastal wetlands in their national inventory of greenhouse gas emissions and sinks, this provided an opportunity for states to incorporate specific measures related to coastal habitats into their national working land strategies. States need a lot of help in this, but there's growing interest for the climate mitigation benefits, but also because management strategies related to conserving and restoring these habitats can bring about significant co-benefits. For example, helping with flood mitigation, shoreline protection, water quality improvements, providing habitat for fish and wildlife, and opportunities for recreation. So we are engaged in several states, and each state is different, but I would say across the board, we kind of focus on four primary areas. One is acting as a convener, where we try to connect coastal wetland researchers and managers on the ground with climate planners and create those bridges. Often climate planning takes place in the context of a air quality office or something, and so kind of staff there may not have knowledge of coastal ecosystems and climate contributions. We also provide targeted support for data and science to address key management needs and questions, in particular to help inform the development of state inventories, blue carbon inventories, and to inform setting of targets by looking at scenarios. We also do a lot of work just communicating about blue carbon, what it is, why it's important to really elevate the issue. And finally, we engage in policy advocacy. We advance science-based policies to secure new management measures to better protect and restore these ecosystems, and to derive new funding sources to support this work. So the chart here on this slide just is an example of some of the research that we supported, which was done by Jim Holmquist from Smithsonian Environmental Research Center, that looks at the state of blue carbon data and assesses this based on the Coastal Carbon Atlas. All right, so Pew, we are currently engaged in California, Oregon, and North Carolina, and we are beginning to engage in New Jersey. And all of these states are in the process of developing research and developing management strategies related to blue carbon as part of their climate planning effort. I'll just note as well that Maine, Maryland, and Louisiana have done some great work on blue carbon in the context of their climate planning. So just to give an example of what this looks like at the state level, here's an example from California. So in California, the Air Resources Board adopted their 5-year climate change scoping plan late last year, which for the first time included specific targets in the natural and working land sector. And this scoping plan is basically the roadmap for the state as it works towards achieving its goal to reach carbon neutrality by the mid-century. So based on inputs, expert input, convenings, research, and a significant amount of modeling, the state came up with these targets. And I'll just flag here the one that they put forward related to wetlands. And this acreage target includes tidally influenced wetlands in the Sacramento-San Joaquin Delta estuary. And the greenhouse gas mitigation benefits of this work, it could be quite significant. This is a highly altered ecosystem, And so restoration work could help reduce emissions currently happening in these degraded wetland areas, as well as restart carbon capture and burial. Oregon as well has been an early adopter of blue carbon in its climate planning. In Oregon, the Global Warming Commission developed a natural working land proposal and is now for the governor and is now developing a specific plan for implementation. Pew partnered with the Pacific Northwest Blue Carbon Working Group, and Laura Brophy is part of that working group, Sylvestrum Climate Associates, and the Oregon Coastal Management Program to develop a specific blue carbon strategy that the Global Warming Commission then incorporated into its proposal and is moving forward in its plan. So a key centerpiece of that work was the development of a greenhouse gas inventory for Oregon's coastal wetlands. And this was important for several reasons. One, it demonstrated that this could be done, that there is sufficient science and methodologies available for states to do greenhouse gas inventories of their blue carbon habitats and incorporate it into their broader inventories. Second, it showed quantitatively that Oregon's coastal wetlands are a net carbon sink and therefore should be included in natural working land strategies for climate mitigation. And finally, it provided a scientific basis for policy recommendations that were put forward and that are now being considered by the state. And these include protecting existing coastal wetlands from further loss, planning for future sea level rise by protecting areas that will allow for coastal habitats to move inland, and looking for those high leverage restoration opportunities. And in Oregon, in particular, forested tidal wetlands are of big interest, and Laura will get into that more in her presentation. We are mainly focused on state-based work, but are starting to engage nationally. We recently launched our Blue Carbon Network, which is a forum for states and regional blue carbon researchers and practitioners to learn about emerging research, share information, and discuss management strategies related to blue carbon. And I'd also like to flag kind of opportunities at the federal level. The Biden administration has prioritized blue carbon in several of its signature policy initiatives. Most recently, I think it was in March of this year, the Biden administration released its Ocean Climate Action Plan. And this plan has a specific section related to blue carbon that lays out recommendations and priorities, and also includes agencies that can help move those priorities forward, including NASA. So I'll just share some kind of hot topics or hot button issues that we hear about a lot in our work in the states. One is really a need for mapping, refined mapping and change over time data for the states. Secondly, a big topic is how to understand and manage sea level rise impacts on coastal landscapes. What happens to coastal wetlands when they drown because of sea level rise? What happens to that carbon? And how can states look comprehensively at coastal adaptation and resilience strategies with carbon management strategies to kind of mitigate those carbon losses? States are also interested in having quantitative assessments of the many benefits that coastal wetlands provide, in addition to carbon, such as flood mitigation, biodiversity, water quality, and are there ways that these benefits can be looked at in kind of a stacked way? And finally, interest in other habitats, wetland habitats with greenhouse gas mitigation potential, such as peat wetlands or forested wetlands, and looking a bit more near shore and offshore. What about oceanic carbon? And kelp in particular is a hot topic. All right, so before I turn over to Laura, I just wanted to briefly touch on work that Pew's International Coastal Wetlands and Coral Reefs Project is doing. I do not work specifically on this project, but I'm happy to connect you with the team if you have questions about this work, but I thought it would be interesting, of interest to this community. So the International Coastal Wetlands and Coral Reef Project works at an international level to help countries include coastal wetlands into their nationally determined contributions under the Paris Climate Treaty. And this work looks similar in a way on a much bigger scale to what my team is doing on the state level, where they're working with countries to help develop carbon estimates of their coastal wetlands, and then use this as well as commitments for greater protections for nations to put forward under their Paris Treaty commitments. So currently, this project is working in Belize, and they are in the process of expanding to 5 additional countries, and we'll be announcing this soon. A new effort that they are beginning to launch as well, which I thought would be of interest, is a major effort to map seagrasses in the Western Indian Ocean. So the idea here is to develop a standardized seagrass map for the region with field verification, and to use this mapping to raise awareness among countries in the region and to help them include seagrass protection measures as part of their Paris Treaty commitments, and then to just generally increase capacity in the region to better map and manage seagrass habitats. So with that, thank you again for the opportunity. I will stop sharing and we'll hand it over to Laura.
Thank you, Sylvia. I'm going to locate the correct screen here. So, does that look good to you all, Adel? Can you confirm?
Yes, it looks good.
Sharing. Thank
Yes.
you. So happy to have a chance to talk with you today about some of the data gaps that remote sensing might be able to help us fill to advance our blue carbon work and coastal wetland management more generally. Tying into Sylvia's talk, I want to touch on how remote sensing might help us avoid further loss of coastal wetlands, protect these landward migration zones, and both locate and help restore forested tidal wetlands that are such a high priority now in a number of areas. And remote sensing can help us improve our mapping and change analysis. That's been a huge focus of my own work. And remote sensing, I think, also could help us do a better job of accounting for these co-benefits, for example, by more efficiently mapping and modeling some of the key drivers for these functions. Co-benefits, in fact, are the main focus for a lot of the stakeholders that I work with regionally and nationally. So I feel it's going to be a great win-win for everyone, and working with you all to improve our use of remote sensing could really have very broad benefits. So these are the 3 data gaps that I'll talk about today. There are many more. First, accurate mapping of our blue carbon resources, as Sylvia mentioned, is vital. And this actually is the area where we've made some pretty rapid progress recently. And I'll tell you about that. And second, we really need to do a better job of mapping potential restoration sites and assessing the effectiveness of the restoration that we conduct. And third, salinity is a huge data gap, and interested in hearing from you all and having further talks about how we might use remote sensing to address this gap. I'll start with the blue carbon resource mapping, especially those critical forested and shrub tidal wetlands. So we map all tidal wetlands from ocean to head of tide and consider them all blue carbon resources. Of course, you have to account for greenhouse gas flux, etc. Salinity is not a factor in the definition of our mapping of the estuary. We include all tidal wetlands, including the freshwater tidal zone. And we found that it's been important to adopt a consistent nationwide definition for tidal wetlands. And specifically, these are those wetlands that are inundated due to tidal forces at least once a year. And this is a definition from national hydrogeomorphic classifications developed in the 1980s and used by many states in their coastal land use planning and regulatory activities. So blue carbon resources include all vegetation types as well as unvegetated mudflats, etc. So we're looking at everything: eelgrass, marsh, shrub, and forested. And we also want to map these diked, disconnected former tidal wetlands, which represent restoration and climate mitigation opportunities. So we've been working for about a decade now to improve our tidal wetland maps for a couple of big reasons. The standard for mapping blue carbon resources in most states has been the National Wetland Inventory. It's a wonderful resource, nationally consistent. It doesn't capture several kinds of information that we need. Tidal marsh is visually distinct in aerial photos, which are a key part of the process for NWI. But tidal swamp, which is a real blue carbon powerhouse, is not easily recognized in aerial photos. And it's not really well mapped in the NWI, and in fact, we've had some recent talks with their national leadership, and they agreed these forested tidal wetland ecosystems are challenging to map. So in the middle of this slide, you can see a map of part of the Tillamook Bay estuary in Oregon. And I'm going to focus in on the southern portion, that blue area. It's an agricultural landscape. And this consists of a lot of diked former tidal wetlands. And the NWI maps some of these as wetlands. Often they are not attributed as diked. Some of them aren't mapped as wetlands. So basically, this is a challenging landscape to interpret. And NWI's goals and purpose and mission aren't necessarily to help us with problems like identifying diked former tidal wetlands. Our solution to these mapping problems has come from a remote sensing method that we developed in 2014 here in Oregon. And then I worked with our Pacific Marine and Estuarine Fish Habitat Partnership, or PMEP, to apply these methods to the whole contiguous US West Coast. And basically, we take LiDAR elevation data. You can see the colors in this map. This is that same southern portion of that Tillamook estuary that's ag fields, pastures primarily. And these elevations range from the blue range of about 2 feet and AVD88 up to 14 feet here. And we combined that LiDAR DEM with the NOAA water level data to map the annual high tide elevation contour. And everything within that contour is a part of the estuary, potentially. If it's artificially disconnected, it still is within tide range. And we call this approach the elevation-based estuary extent model, EBEAM for short. So if you hear me use the acronym EBEAM, you'll know I'm talking about that. And we published our findings from this mapping method in PLOS ONE, this is for the West Coast, in 2019. We're currently applying this method nationally at all 30 NERS, National Estuarine Research Reserves, and their surrounding estuaries, giving us a much more comprehensive understanding of the benefits of this approach and its limitations, and we'll be completing this project in early 2024. Referring back to the reasons for our mapping work, you recall tidal swamps are difficult to map, and they're not always well mapped in the National Wetland Inventory. And this national project, its acronym being High Tider, has shown the tremendous advantage of elevation-based mapping for finding these tidal swamps. So this is an example from the Apalachicola River River estuary in Florida. And as you can see from the legend, this cross-hatched areas in this map to the lower right represent areas that are mapped as tidal wetlands, either fresh or brackish, by both the NWI and they're within our elevational boundaries. So they're part of the estuary as per both methods. But the blue areas are those areas identified using our elevation-based mapping, which are not attributed as tidal in the National Wetland Inventory, although many are mapped as wetlands. So basically, we were able, using this elevational method, to identify 23,000 hectares of forested tidal wetlands, which are blue carbon resources in this particular estuary. And this has been true across the nation, that we can better map forested tidal wetlands using this approach. The other major motivation for our mapping work has been to accurately map diked former tidal wetlands. These are our restoration opportunities. But this does represent a large data gap, and I'll explain why. So within this elevational boundary, we know that everything is within tide range, but some of these areas are diked or disconnected, mostly due to human alterations to the landscape, as I mentioned, like dikes, but might be roads, filled lands, and so forth. There's a lot of interest in identifying these areas accurately. For instance, these areas are often difficult for fish to access, and that greatly reduces their fish habitat functions. So fish biologists want to know where these disconnected areas are. And we held a symposium and workshop on barriers to tidal connectivity in 2020 with our West Coast Fish Habitat Partnerships. And among the next steps that were identified by the group relate to science gaps that need to be filled, data gaps in other words, and one of the highlighted needs was to test remote sensing methods to map and quantify tidal connectivity. So using, just as a baseline, our elevation-based mapping, I want to show you how powerful remote sensing can be in answering these questions. So this map illustrates the Coquille River estuary in Oregon. It's the river flowing to the Pacific at the left, and you can see the broad bay. These are the areas that are identified by the National Wetland Inventory as tidal at the time of study that we did, just a couple hundred hectares. when we apply our elevational boundary, we are able to quantify the impact of diking because we can identify 3,300 additional acres of diked former tidal wetlands. It's a very important method and has really advanced our planning. We also have used other resources to figure out the historical habitat types present, and most of this was tidal swamp. So this kind of use of elevations has allowed us to do these studies that have basically elevated tidal forests to the forefront of much of our prioritization for restoration in the Northwest. This bar chart shows that in Oregon in the 1800s on the outer coast, we had about 15,000 hectares of tidal wetlands, and over half of them were tidal swamps, i.e. forested, primarily forested tidal wetlands. We have only about half of our tidal wetlands left in Oregon, but we've lost 95% of our tidal swamps. Very disproportionate loss. And that's so important because of their historical importance. And that's true throughout the Pacific Northwest, by the way. And as Sylvia mentioned, these tidal swamps store a lot of carbon. So on the right, you can see a bar. This is a bar chart from our 2020 publication about carbon stocks. And Pacific Northwest tidal forest exceeds the carbon stocks for almost all other tidal wetland ecosystems globally. Mangroves are the only ones that come close. So you might be wondering, how did we determine these wetland losses? And the best approach is what I call a direct loss assessment. We need to directly map those areas that have been lost from the estuary footprint. And we've done this in Oregon, Washington, our team in Oregon and others in Washington, by analyzing topography with digital elevation models, with a lot of expert input and hand digitization. This is a method that works very well to produce high resolution results, accurate for local planning purposes, but it's not easily replicable or scalable, not easily updated. And this is where I think remote sensing comes in. We want to improve our consistency, our comprehensiveness, our replicability, our scalability in mapping these disconnected areas. I feel the important goals here are high resolution data that can be used nationally and regionally for consistent comparisons, and maps that can be updated as conditions change. And also, as a goal, I would like us to be able to quantify the degree of connectivity. That's important for measuring restoration effectiveness and understanding impacts. So just to show a couple of on-the-ground images from aerial photos, I want to begin talking some specifics about remote sensing approaches and what they might look like. And three approaches that I want to consider, and I'm sure there are others, would be a time series analysis of changes to water or inundation, water surface elevation discontinuities, and channel morphology. Starting with time series analysis. This analysis would be conducted within that elevation-based estuary extent. And that's actually true for all three of these approaches, because that's our very important first step that draws sideboards on what we need to analyze and prevents malfunctions of the analytical approach. We need a time series of classified imagery, and cells that are classified as water are the focus of the analysis. Tidal wetlands will have cells classified as water or inundation that blink on and off with the tide signal. So in other words, their blinking periodicity matches that of the tides. In diked or disconnected former tidal wetlands, those cells classified as water would be more static. They would change, but they wouldn't change with periodicity matching the tide signal. And of course, you all are probably familiar with Jim Holmquist's very cool work on this topic under your funding as well as NOAA's. And he's worked with others to produce this tidal surface water index. Now, this is an exciting approach, and it has the big advantage that the degree of connectivity is theoretically classifiable. And that would be by looking at, the degree of match between the location of interest and known tidal wetlands. So, show this in a sort of a proxy way. Restored tidal wetland is at the top of this image, and the lower half is a diked area. And low ground in the restored tidal wetland, these are sort of pond areas at high tide, and they empty at low tide. In other words, they'll blink on and off with tidal periodicity. And the diked areas, even lower, don't fill with water because it's diked, and they're protected from inundation. With high, a classified image. and the change will be visible. And as I mentioned, tidal areas that are partially disconnected or have less than 100% match are what we would call muted areas, muted tidal. Their degree of connectivity is going to relate very closely to functions. And in restored tidal wetlands, we should see a pattern that matches known tidal areas. And we could, in theory, quantify our effectiveness in restoring these sites by evaluating the degree to which the pattern matches a known tidal area. We also could determine the date of restoration by looking at these time series. So the next possible approach would be looking at water surface elevations. This analysis, again, is conducted within the sideboards of our elevation-based estuary extent. We need a remotely sensed water surface elevation. I don't think LiDAR is our best choice because we need something that's flown frequently, like satellite imagery, maybe altimetry. I'm really looking to pick your brains on this. This analysis theoretically doesn't require a time series, but because the discontinuities might not be visible at all tide levels, we would have to analyze and scan a number of images to choose the correct ones, and we probably would use multiple images. You probably can't quantify the degree of connectivity, but that's yet to be determined. In a tidal wetland, the water surface elevation would be fairly continuous, fairly level. In a diked or disconnected former tidal wetland, the water surface elevation will change abruptly, often will change abruptly at low barrier. And the best data would be from mid to high when channels aren't empty. So as in Oregon, these are primarily diked areas, but within the river channel in the center left, you can see tidal, and I'm on that area. So you can see that in that tidal well, which is an island, the green channels coming in from the elevations that are in the but to behind dike surface elevation indicates a flow barrier. Now, the third approach could be to look at channel morphology. Again, conducting this analysis within the elevation-based extent. No time series would be required in theory. Both digital elevation model and visual imagery would probably be useful for this analysis. In tidal wetlands, we usually see a channel width that tapers gradually, at least in the less disturbed systems. The channels are generally curving and sinuous. In the diked or disconnected or altered former tidal wetlands, the channels are often straight or ditched, and they often have sudden width discontinuities due to turbulence pools or alterations. And those are associated with the flow barriers, which can be visualized in the digital elevation models. So as an example, again from the Tillamook Bay estuary, we have mostly tidal wetlands in this image, but to the lower right, you can see a diked former tidal wetland. And the channels are meandering in the tidal wetlands. There's a varied degree of meander depending on landscape setting. But in the diked area, they're quite straight. Ditches usually are. And then again, if we look at, oops, I skipped over one. The channel width also are generally tapering gradually in the undisturbed tidal wetland versus sudden changes in channel width at flow barriers for diked areas. So each of these methods will work better or worse depending on local conditions. And as a result, I think most likely a combination of analytical methods is most likely to be successful. And I really do think there's huge potential here for sort of a machine learning or artificial intelligence approach combining these different methods. I think that collaborative and iterative methods development will be essential with initial small pilots to test different ideas, and validation through local review in different regions of the country will be very important. And I mentioned, and I'm almost done here, but I just want to quickly mention, we want to do these analyses within our elevational boundary of the estuary because it helps us avoid problems with the methods. They won't work well in non-tidal areas. We haven't done our elevation-based mapping for all the coasts of the US yet. We've got pieces of each coast. We've done the whole West Coast. Luckily, there is another resource available that we can use to get at this elevational boundary, and that's NOAA's high tide flooding layer. So here I'm showing that blue, that's our elevation-based estuary. This is a flooding layer, which was about the time we were project nationally and being released. That these two layers align really well, which makes sense. NOAA's high tide flooding and specifically the minor flooding scenario. indicates areas that are likely to inundate a few times, a handful of times per year. But we would expect that would align well with our elevational boundary based on the tide, and it does. It's a surprisingly close match. So I would highly recommend NOAA's high tide flooding data sets as base layers for any of these analyses we're discussing. And I'm going to talk super briefly about salinity because I honestly don't know how high the potential is here, and you all will have better knowledge. We have such sparse salinity data for estuaries. Most estuaries have no modeling and no systematic sampling programs. We need data on salinity for so many reasons. Of course, for greenhouse gas flux and climate forcing analyses, for understanding the landscape distribution of tidal marsh versus tidal forest, and that would allow us to choose restoration sites appropriately for those different goals. Wildlife support is very dependent on salinities, such as salt adjustment for young salmon heading to the ocean, and of course, human needs like drinking water or agriculture are very dependent on salinity versus fresh. The landscape array of habitats within our estuaries historically depended strongly on salinities, with the swamps being found up estuary and the marshes being found down estuary where salinities were higher. But we can't assume that our salinities are the same now as they were back then due to the many alterations to our estuaries. So we need salinity maps to guide our restoration activities. Field monitoring is labor intensive. Sensors are susceptible to biofouling. There's a huge amount of temporal and spatial variability on multiple gradients within our estuaries. So you have to have quite a spatially populated sampling array to get good data. And modeling is great. Hydrodynamic modeling can produce wonderful results, but it's difficult to parameterize and expensive, and there's little potential for applying that across all coastlines. There is a potential for reduced empirical models, but they might be fairly estuary specific. There are various approaches for remote sensing of salinity. Vegetation proxies could be really useful where you know the thresholds between different marsh types, for instance. But we don't have added to use for forested tidal wetlands. And also using a vegetation proxy gives you pretty limited ability to address the temporal and spatial variability and salinity that's so important in greenhouse gas flux models. Direct remote sensing of salinity is what I would love to learn more about, help determine thresholds for these priority ecosystems and support our restoration planning. This approach would make no assumptions, and it would allow us to measure temporal variability and spatial variability directly. There will be challenges in resolution and accuracy. I know some of these recent publications highlight these significant challenges, but I think we need to be talking about this. So I think it's time to start our discussion, and really looking forward to your questions and answers. I've seen a few coming through, so I'll stop sharing now.
Thank you, Laura, and thank you, Sylvia. That was a lot of like very relevant information, especially for this CMS and the carbon community here in CMS. So thank you a lot, Sylvia and Laura. And then we have exactly, as we planned, a little bit more than 15 minutes for the Q&A. We'll go to the questions in the chat, so please post your questions there, but also we'll give time for people to unmute and make their questions directly to Laura and Sylvia. So I don't know if, Sylvia, do you want to add anything else, a little bit more context to the first question from Doug regarding how do we get blue carbon benefits to count within the U.S. Clean Water Act and the Rivers and Harbors Act context, which still largely only consider fish and wildlife support and navigation?
It's a good question. And Doug, I think there's some interesting work coming out of CEQ looking at this as part of their natural climate accounts. I don't know if you know, Lydia Orlander has been working on this, so I can follow up with you to see. But I think from a political perspective, as we all know, it would probably be a tough road in Congress to get that added. And I'll post a bill in the California state legislature, though, that does incorporate blue carbon into their permitting under the Coastal Act, which is kind of illustrative. I think more traction could be gained at the state level for this at this point. But
Great, thank
I'm
you.
not an expert on it, but that's my off the cuff.
Thank you, Sylvia. And Doug also had a question, this one for Laura, regarding the e-beam method. Can it be combined with sea level rise projections to identify marsh migration corridors? And if so, will agricultural dish networks confound that analysis?
Thank you, Doug. There's not a problem with ditch networks confounding the analysis in my experience to date. We do use e-beam as our boundary for getting the time zero conditions, and then we move that boundary upslope with sea level rise increments. So it's basically identifying an area. And of course, this works for the tidal swamps as well as tidal marsh. So yeah, it's we're really advocating for the use of e-beam as the baseline for those time series sea level rise analyses.
Thank you.
Welcome. And we've done that in Oregon, by the way, comprehensively. I didn't have a chance to talk with you about that project, but yes, that's been completed.
Thank you, Laura.
Welcome.
We have here a couple of questions from Domber Carpenter. Domber, I think, is one of our stakeholders from the Northeast, I think from the state of Massachusetts. And he mentions, to account for forested wetland carbon stocks and fluxes, have you given thought to how methods typically used to assess forest carbon can they be combined with methods typically used to assess wetland carbon? Perhaps wetland-oriented methods will be used for soil or below-ground pools fluxes, and forested methods for live or above-ground vegetation biomass.
I think that the methods we've been using to date in the forested wetlands in the Northwest have combined such methods, but I'm not an expert on forest carbon plot-based inventories, so I would be interested if any others who are on the call, Amy Bordy, I think I saw might be here, could potentially address that question. But basically, I believe we are combining these above ground inventories and stock assessments with the below ground in that case.
Hi, Laura. This is Amy.
Hi, Amy.
Hey. Yeah, that's exactly right. The methods to combine both of those are in process for the work that we've been doing right now on the West Coast. So taking the gas flux inventory data and the carbon stock data and combining that to get a net ecosystem carbon flux estimate at the ecosystem scale. And then once that is done, then that can be applied to these mapping methods to get more complete inventories.
Thank you. I want to comment on the salinity comment that someone made, relevant data on salinity and their variability within estuaries at the Coastal Salinity Index from USGS. And yeah, these are the types of data we need. It's just the resolution in order to choose a restoration site within an estuary, when most restoration planning is done on a site-by-site basis at a scale of looking at a few hundred meters, and how salinity might vary across a kilometer or less of the estuary, up estuary in river systems. We have we have some challenges with resolution for analyzing salinity for sure. But this is the type of broad approach I'm interested in.
Can I add one more thing? Just thinking about that. Sorry.
Yes, sir.
Yeah.
Just on the inventory basis of and remote sensing, I think using some of the LiDAR-based methods for really understanding biomass, particularly in these forested areas, is very relevant, because we don't necessarily have great data from just forest allometry data to estimate what the biomass is in some of these forested wetland areas, and LiDAR could be used for that also, to get that estimate.
It's a very good point.
Okay.
Allometry could really differ between wetlands and upland forests as well.
Thank you, Laura and Amy. Now we have time. We can open for people that want to make their questions, comments directly to Laura or Sylvia. Please, either you can raise your hand or you can unmute and make the question directly to them. Let's see if we have anyone. Okay, I see Asmati. You have your hand raised. Yep. Asmati, you can unmute yourself.
Yeah. Thank you very much. I would like to know how to measure the change of the coastal lines because it is important. And many people in Indonesia doing their projects makes the dikes in the coastal to the agriculture maintenance and peatland inside is the problem too. And how to measure the carbon too, blue carbon, if the change of the coastal line. Thank you.
The shoreline, in other words.
Yes.
I think that this is amenable to any number of analytical approaches, and I wouldn't want to step in and suggest what NASA might have been doing along these lines. I'll bet that there's been some activity. Does anyone from NASA have comments on how you've been approaching those questions of shoreline alterations broadly, or shoreline change?
Yeah. Because in Jambi province, the east coastal, the shorelines maybe change because my student doing research about that. And blue carbon too, carbon stock exchange too, because many the mangrove lost. Yeah, thank you.
Oh, yeah. So with Muddy, we actually, for our change analysis for the state of Oregon, we were able to quantify seaward advance of tidal marsh across the 150, 200-year period. And I can send you, I'll put in the chat a link to that study. So, and in the same study, we could also quantify retreat, although that was not occurring on our coastline to any great extent. So some of the methods we've been using might be useful to you. So I'll pass along that particular document.
Thank you.
Thank you, Laura, and thank you, Asmari. Asmari, I think, is joining from Kalimantan, Indonesia. So thank you, Asmari, for joining in because I think it has to be very late there.
Yeah.
Are there any other questions, comments from people joining online? Doug.
Yeah, sorry, I didn't want to monopolize with all my questions, but something that's been coming up in Maryland as we're considering a Chesapeake Bay blue carbon pilot is that the ownership between private land and public land changes as sea level rises. And this might be a very interesting problem for blue carbon projects going forward. In that, you know, the real property holder, the guy with the paperwork that says I own this, is going to be underwater, but the states have not yet resurveyed or claimed, you know, ownership of public land that is now submerged. Have either of you seen in the context of a blue carbon project, folks wrestle with this? And you know, to whom does a conservation easement get paid? To whom does the carbon accrue? Have any of those questions been tackled yet by folks who are further along in the blue carbon space?
Sylvia, do you have an answer on that one?
Well, I don't know if it's an answer necessarily, and Doug, you're probably aware of this, given it's right next door in Virginia. But you know, some states have passed legislation enabling carbon credits on state submerged lands. So that doesn't get at the issue as what you said in Maryland, where they actually need to assess and claim ownership, but there have been efforts to enable carbon credits to be secured on state land. So
yeah, sorry, Sylvia, just to clarify, this is as you go into the future in your, change in sea level is now inundating places that are currently considered private land. So I understand what Virginia's doing for existing state-owned submerged lands, but what about future state-owned submerged lands that are currently in private ownership?
Yeah, I am not aware of any project to look at this in the blue carbon context. I know not to keep quoting California, but you may be aware that they are looking at this issue as it relates to sea level rise and the public trust doctrine and how that relates to Coastal Act authority. So that's off the top of my head, that's the only state that's kind of looking at that issue of private lands becoming public lands due to sea level rise.
Thank you. And if maybe offline we could follow up any specifics on that California movement would be really, really helpful. Thank you.
Sure.
Thank you, Doug. We might have question for time for one more question or comment. And if there is no question, I was going to make a question. I think more towards Sylvia, because you mentioned a couple of organizations, stakeholders that you're working with, especially the U.S. Climate Alliance. In some of the different projects that we have, we're working with the U.S. Climate Alliance. We're working with a lot of the states, especially in the Northeast, mostly on forest carbon monitoring and how to monitor forest carbon. There's always a lot of things, a lot of work projects that are happening. So I was going to ask you how to better coordinate the work that is happening across all of these organizations, state agencies, even federal agencies, regarding the mapping of blue carbon. And if you have any comments on who are the stakeholders that are missing, who are the stakeholders that we haven't engaged. We're talking about U.S. Climate Alliance. We're talking about state climate agencies. But who else should be engaged? And I think this is important for our end as we're engaging with different stakeholders and also for the different scientists that are also engaging with stakeholders.
That's a great question. I'm sure Laura has some thoughts on this as well. I mean, I would say to your first point about coordination nationally, yes, I agree. And in fact, in the Ocean Climate Action Plan, that is a recommendation that there will be greater coordination, at least amongst the federal family of agencies. Now, how that will be implemented, I don't know. Maybe some of the federal partners on this call have some insight. I do know that the Restore America's Estuaries was convening a national blue carbon working group and are hoping to get more active in that as well too. So stay tuned for that. And basically the purpose of that is, as you said, bringing together kind of the key federal agencies that are doing research and policy in this space to kind of work together. Who is missing? I mean, that is a good question. I don't know if I have a great answer to that. I guess I would just note that, these changes along the coastline that are impact carbon and resilience and whatnot, obviously frontline communities. And I know sometimes discussions around carbon can be pretty, I don't know, kind of maybe not on the ground, but I would just flag that. And I guess just because to my point about kind of merging some of these discussions around carbon and blue carbon with resilience and adaptation as well. So maybe some of the groups that are more engaged in that space, I think those of us interested in blue carbon could learn a lot from them and vice versa. So I would just put that forward. And it looks like Laura has some other additions.
Thank you. Thank you, Sylvia. And Laura, anything from you and any last thoughts as we're working?
Yeah, I think in terms of who might be missing, not having participated, not sure who all's involved, but who might be missing. I work a lot with organizations that map and manage wetlands. I think all of those organizations could do a much better job coordinating. Examples would be Fish and Wildlife Service with the National Wetland Inventory, NOAA with its Coastal Change Analysis Program, the Army Corps with its regulatory duties and its mapping is integral to all of their activities. State wetland programs, EPA for its change and trends analysis. All these organizations we're using different methods of mapping wetlands, but I think we need to align.
Thank you for that. We hope that we can continue this engagement. As I mentioned, we have a couple of events, efforts coming up, and we're more than happy, Laura, Sylvia, that you can join us as you can in these efforts. I see that Lola Fatoyimbo, she is a wonderful person. She has a lot of work mapping wetlands using different remote sensing techniques, especially, and I think you mentioned, Sylvia, this project in the Western Indian Ocean. So I saw that Lola mentioned that she was going to be reaching out to you all by email. So thank you for the time again. We'll be posting the recording and the slides of this talk in the website carbon.nasa.gov later in the week. So hope that you can join us in the next CMS Policy Speaker Series. I think it's in exactly 2 weeks, so we'll send more information about that. So thank you again, everyone, and thank you, Sylvia and Laura, for your time.
Thank you so much
Thank
for
you.
organizing and everyone for attending.
Thanks for the opportunity. Bye-bye.